Good morning, everyone. Our senior Capstone design project is on Radiation Assessment Rover, also known as RAR for short. So this is our outline for our presentation today. We're going to go introduce our team members and go all the way to process information, to standards, and actually code of ethics to the conclusion. My name is Karthik Madur. I am the project lead.
My name is Taesu Lai. I'm electrical engineer.
My name is Franz. I'm the computer engineer.
And we are collaborating with mechanical engineering team. And these are the members of a mechanical engineering team. And they are Kishan, Joseph, and Michael. Kishan is the mechanical engineer lead.
So why did we choose this project? This right here is our #1 motivator. This is a Fukushima nuclear power plant in Japan, and it unfortunately encountered an energy crisis in 2011. So what happened was basically the tsunami struck an island, and soon after an earthquake followed. But right after the earthquake followed, the fission reactors, or the active reactors, were supposed to begin their cool down process. But unfortunately, since the tsunami disabled their emergency power systems, they weren't able to do so. So with the improper cooling and that basically made development happen.
So nuclear and radiation accidents and incidents are measured in International Nuclear Radiological Event Scale, INES, and it's on a scale of 0 to 7. And 0 is deviation, from 1 to 3 is incident, and from 4 to 7 is accident. Here we listed a few of disaster and accidents that happened in the past. From 1952 to 2011, there were total cases of 29, and among them, Chernobyl, Ukraine, and Fukushima, Japan are the worst cases, and they are on the level of 7. After every nuclear and radiation accident, we need to clean up the contamination that causes, and we need to stop the leaking if there's leakage inside, and it's the most important job. And we, as human beings, cannot go into the radiation zone because it's very dangerous. So this is where the robots became critical. And scientists and engineers will be benefited from it because they can learn what's happening inside and can prevent the future, happening more disaster in the future. And also, war environment will be benefited if we can reduce the contamination as soon as possible and as much as we can.
Here we have our criteria ranking of the needs, and this matrix we actually use this to help us determine which specific criteria that would make our project more successful in contrast to past projects that we looked into. And what we found out was that scalability is a criteria that we would need to focus on for our project to overall be successful in contrast to others. And next slide, where we talk about the engineering and marketing requirements. When you're developing a project, when you're selling a product to a customer, it's important to take into account what is going to be beneficial to them. And to our case, what we mainly look into were 3 things, which was the performance, the safety, and the maintenance. The reason we focus on those 3 is because we're going to be creating a system that's going to be performing complex operations. So we want to create a system that is able to keep up with all the functions that is going to be required by the customers to perform, which is why performance is our top one. And we are going to be dealing with radiation, so we want to create a system that is easy to maneuver, and because since you're going to be dealing with radiation and you can't go to these zones, you're going to need to control that system from elsewhere, which is why we incorporated the ECU software where you would be able to control the system through a wireless controller. And the maintenance comes to account because we want to create a system that is long lasting so that it can be used for various nuclear plants or any disaster zone that it's going to, because we're not creating a system that is only going to be used for one project and then it's just done. Here what we have is our engineering trade-off matrix, and we use our matrix in the last 2 slides to help us identify the positive correlations that we're going to see, and that would help us show positive correlations that the criteria have upon each other. And what we have is the arrows pointing I mentioned before, we figured that scalability is going to be the most important criteria. Now that we narrowed it down to scalability, we had to find 3 categories where we would, where that would help us achieve that scalability that we would need. And the 3 things that we focused on was the ease of the installation, the functionality, usage, and the portability. And the reason we focus on those 3 is because we want to create a system that is easy to be implemented, and when a natural disaster happens, it will be ready to be deployed and head there. And the functionality is also important because we're creating that system so that while it is performing in-depth calculations in itself as it's going to those places, you want it to have basic functionality so that anybody can use it.
These are 2 of the existing projects, among a lot of existing projects. And Mini Memo is the first one that actually reached to the #1 power plant in Fukushima, Japan. And it's only 30 centimeters wide, and it can swim. And Sakura is basically built for the underground facility. It did not go into Fukushima, Japan. It's just built for the disasters. So what will RAR look like? It will have camera, resistant, radiation resistant body, wheels, and sample collected arm.
So here, what we have is our behavioral module, and we broke it down into the most basic form so that you're able to understand it. Is that we have it set up so that our system is going to contain sensors and controls that are going to be operated by the operator. And then next slide, where we see our function module. So the way we broke this down is that we have it set up so that you can see how our electronic components is going to be communicating with each other. And in that case, you have the battery being supplied to the microcontroller, and the microcontroller gains access to all these different components, such as the sensor, the camera, the motor controller, and based on whichever function that we have is what output is going to give. So in the next slide, where we have in our system algorithm. So our system algorithm, that's the foundational basis of our system, and it pretty much shows exactly how we're going to be using our system from where it's going from point A to point B. So the way that it starts is that when the battery supplies power to the system, it sends a binary signal 1 to the user so that the user gains access to our system. That means that now it has access to the 2 microcontrollers that we have, which would be the Arduino and the Raspberry Pi. And the Raspberry Pi is used to give us a video output because we want to see where our system is going. And Arduino is used to account for the sensors and the GPS and the motor controller. And we do notice that since we're going to be dealing with radiation, we want to have a way for our system to know when the radiation level is too high so that it doesn't go there and our electronics are fried. So what we have set up is before it goes to the target that it needs to go to, it checks to see if the environment is safe based on the radiation sensor. And what we're planning on using is actually a machine learning algorithm. It's an area of machine learning algorithm called reinforcement learning. And through reinforcement learning, we're going to incorporate the Bellman equation, which will help our system expect what is going to happen if it goes into that radiation zone. And the next equation helps the system understand why it shouldn't go to that and the action that it needs to take to prevent it from going to that target. And the last equation is the SARSA equation, which stands for state, action, reward, state, action. And the way that it works, it pretty much helps. It's going to set up an update. It's an updated equation so that our system will learn over time that as soon as it senses it, so that it just doesn't go in there and that it should avoid it.
So what is a radiation assessment rover? Radiation stands for radiation resistant, radiation level detector, and assessment stands for camera for mapping, wheels for moving, and rover stands for autonomous function and durable physical design. So in this semester, we picked a motor, and to do that, according to the design that we came up with in the beginning of the semester, we had torque calculations and speed,
are the system design description, and as we're going more in depth into our project, we had to take into account two important factors that we believe that is going to help our system overall functionality be great. And the two important keys that we focused on was the database system and the system managers. And for the reason why we're incorporating the database system is that the main purpose of our project is to go to these places that we're not able to go to and collect sample information. So when it's collecting those sample information, we want our customers to be able to access that information, and so that it doesn't need to wait for the system to go back from the point that it is, so that you're able to use those information as soon as you get them, and you're able to start implementing whatever course of action that you need to take for you to go to these places and try to fix them up.
One of the most important things the system needs to know is when it's too much radiation for the rover to handle. So when it encounters that situation, it would let the operator know that it's too much radiation, that to pull back. So the operator should pull back the rover, appropriate it with the right equipment, and then put it back into the field. And this is our testing plan. It ranges from the schematic plan to the programming test all the way to the final test. So the first three tests are going to be unit testing, white box specifically, and the full test is going to be like integration test, black box specifically, and the final test is going to be an acceptance test, black box specifically. So our two milestones that we set for ourselves in the beginning of the semester, this is for just the programming and the electrical side. The programming just to get the DC motor running, and the electrical perspective just to get all the components that we need. And this is a lot harder than it sounds because we are working with mechanical engineers, so we have to go back and forth with picking the parts, make sure it aligns with their standards, and then we need to make sure that it aligns with our standards. This was our demonstration video. This is basically what this was made in CAD software, and if the video plays, you can see that. So it can go over obstacles, and as you can see, there's like a big black box in the middle, which will be 3D printed, and inside all of our electrical components are there. So in order to be radiation assistant, just the black box can be substituted with the light box, therefore no radiation can get into there. This was our timeline for the fall semester, and as you can see, like I said before, we have all the components that we need, and after that, everything is going to be happening in the winter semester and the spring semester. And spring semester, we're going to basically focus on building, and fully programming on Rover. This is our cost of materials. So it ranges from control board to the radiation detector, all the way to the motors within coders, so that we know what location they're in at what moment. And this is just some of the IEEE standards and constraints that we have. One thing to note is one of the most important constraints is timing and cost requirements. Timing because we have to work with other people that have a whole different schedule rather than us, and cost because all of the radiation hardening costs a lot of money. One of the things that we always express is ethics, and we follow the ethics instructed by IEEE. So one of the most important things that we do is be honest with our real data and to our teachers, our professors, and our community. And another thing is we don't infringe on any other data that's out there, and if we get anything, of course, credit them the need. And our project is basically made to save lives so that scientists and people don't go into the radiation zones and get affected by radiation. So for future work, like I said before, for the winter semester and spring semester, is to basically get the simulations running for the winter semester, and spring semester is just to build the entire thing and start testing it. And the other important thing to get out of our project and this presentation is that our project is very open-ended, meaning by that this is not just limited to radiation zones, it can go into any disaster places that human beings can imagine cannot get into. So these are our references.
Thank you very much.
Thank you.